This lesson is going to be on forces on inclined planes. We're finalizing our Unit 1A overview, Objective 3, and we're only doing just solving problems involving forces. So we're taking everything we've learned from forces, F equals ma, horizontal vertical forces, and forces at angles, and even forces with pulleys to work on this final piece of Unit 1A. So we have a warm-up in which we've got a box that has a lot of forces acting on it, including a force with an angle. And I want to ask, how do we know, or who do we know, if the box accelerates? And how do you know which direction the box is going to accelerate in? So we know if the box accelerates, right, if the net force is greater than 0. And how do you know which direction it accelerates? Well, we would have to find the component here, and decide if this component is greater or less than 60 newtons, right? So this net force in the x direction, because we already know that the normal force is greater than 0. Since the normal force is greater than 0, we know that it's sitting on the ground or moving on the ground, because it is in contact with the ground. If there was no normal force, then it might be lifted upward. But so all we focus on is it moving in the horizontal direction? So is the net force in the net x direction positive or negative? And so we are taking this force at an angle, and we're like, wait, we don't like forces at angles. We like forces to be perpendicular to each other. So we like horizontal and vertical forces. Now, in this case, we are going to deal with inclined planes, in which now horizontal and vertical forces might not matter to us. We need to instead think of it as perpendicular and parallel. So here's the example we're going to look at. This mass is sitting on an inclined plane that has an angle theta above the horizontal. The only force that's acting on this is gravity. Let's neglect friction just for the sake of ease. And first, which direction can this mass move? Well, it's either going to move down the slope or up the slope. So we're not looking at horizontal or vertical anymore. Which direction must the net force act in? In this case, well, the net force if it's either going down the slope or up the slope, and we've neglected friction, and there's a gravitational force pushing downward, you can imagine that this is going to go, the net force must go down the slope. And so what forces are acting on the mass? So I've already said it, gravitational. And what angles are the forces acting on the mass? Well, that's weird. What do you mean, what forces are acting on the mass? Well, we need to look at this mass and find the components that are towards the direction of motion. So we need to change this to down the slope or up the slope. So we need to tilt your head, right? Tilt your head to the left. So the inclined plane now acts as like a horizontal line. So we're going to look at it kind of like this, where this was our force of gravity. Oh, let's make it over here. This was our force of gravity, because we know that this is going to be moving down the slope. So it must have a net resultant force acting this way, because that's the direction it's going to go. That's the direction it's going to accelerate. So how do we find the components of this gravitational force such that that is the direction of the resultant force? Well, we need to find this component of the horizontal of the gravitational force. So we need to find the parallel component to the plane. Well, if that's the case, if we found the parallel component, that's not all of that gravitational force's components. Then there must be also a what's called a perpendicular component, because it's perpendicular to the plane. So I'm going to call this force, gravity, and then I'm going to put like a perpendicular symbol. And I'm going to call this one force, gravity, and I'm going to put a parallel symbol, which is almost like the Greek letter 2, or just 2 lines. And that's how I'm going to identify this. That's our new frame of reference we're looking at this situation. But we can't always keep our head tilted when working on this, so we're going to go backwards and then try to apply this to our free body diagram here. So draw a free body diagram of the situation. Well, to be honest, the free body diagram is just this. But let's find our components. So we have this component, which is perpendicular to the plane, and we have this component, which is parallel to the plane. So again, FG parallel and FG perpendicular. So where is this angle on that triangle? Right. So let's write FG on this side, because I already said, okay, this is the triangle. Well, this is a right angle, and this is 90. Actually, let's make it not black. This is 90 minus theta. And this angle is 90 minus that angle, right? So this is 90 minus theta. And this is 90 minus theta. So that's just equal to theta. So the angle above the horizontal on this inclined plane is the same as this theta right there. So that's super important, because now we have a angle to this triangle. We know this is a right angle because we have perpendicular and parallel components. So I can identify my force gravity in my perpendicular direction to be Fg times cosine of theta, and I can find my force gravity in my parallel direction to be Fg cosine theta, or sine theta. Gosh. All right. I've missed something here, because what is the resultant force acting on this object? Well, we know that the net force is going to be acting down the plane, so I'm kind of missing something. I'm missing a normal force. This normal force is always normal force always acts perpendicular to surface. But this is really good for us because we already have the gravitational force that's acting perpendicular to the surface as well. It's just acting downward. And so this and this are equal, because the normal force is a reactionary force, and it's reacting to the perpendicular gravitational force to the surface. So this is also equal, in this case, also equal to R. So I'll say just 2 normal force. All right, now let's look at a situation a little harder. Try to make sense of this. So we have a 5 kilogram mass that is sitting on a frictionless inclined plane that's 45 degrees to the horizontal. A force of 10 newtons is pushing this mass block up the ramp at an angle of 30 degrees below the horizontal. We'll have to find out which direction it's going. Therefore, we have to find the net force acting on the mass. So even though the force is pushing it up, it might not be pushing it up the ramp. Let's draw a free body diagram of the situation. So one good rule to draw for free body diagrams is that you should only draw the forces that are acting on the object. So we have a gravitational force acting downward. We have a rightward force kind of in this direction. And that's we'll just call that F. And then there's going to be a R. And we don't know which direction it's going, so we really don't know how big these things are. I imagine R is going to be pretty big though, because we don't know if it's in equilibrium or not, so we can't really draw these lines perfectly well. But that's when drawing free body diagrams of these situations, do not include the perpendicular or parallel components. Only include the forces that are acting on it. So the normal force is acting on it because it's coming from the surface. The gravitational force is acting on it because it's from force of gravity. And this applied force, let's call it applied force, is acting on it to the right. All right, so we know we have this downward force, this rightward force, and this normal force. So that's force of gravity, and then we have some normal force acting upward. Let's now turn our head and look at this and find the components that are acting horizontal to this surface or parallel to the surface and perpendicular to the surface. So let's draw these components. I know that I will have a force gravity that's acting perpendicular. I'll also have a force gravity that's acting parallel. Let's also construct the parallel and perpendicular for this F. So we have a perpendicular component also acting downward as well. And so let's just say F of A, right? This is F of A. Perpendicular. It'll also have a force applied parallel. Let's make that A a little better. And then it also has a R. Now we can actually see what size of the normal force it should be because I've drawn the two downward perpendicular forces from the applied and the gravitational force. And so we know that the reactionary normal force is going to be the sum of those two. Let's see, what other values do we know from here? We know this angle is 45 degrees, and that therefore this is 45 degrees. We also know this angle is 30 degrees. So in order to solve this, it's very similar to the forces at angle situation. We need to find the horizontal and vertical, but in this case, it's parallel and perpendicular. So let's separate that. Let's do perpendicular here and parallel here, and let's make a line in between. All right, I want you to try and solve for all the necessary forces using our sine and cosines and the values of our force applied, which is 10 newtons, and the value of our force gravity, which we don't know, but we do know that the mass is 5 kilograms. So I'm going to pause this video. I want you to try to solve for the components of both the force applied and the gravitational force, and then find the net force in the perpendicular and the net force in the parallel. Well, we should know actually that the net force in the perpendicular is 0 because the R is going to make up, the normal force is going to make up both of those perpendicular components because the object is definitely not falling through the ramp. But I'm going to pause it, go ahead and solve. I'll meet you back in 5 seconds. All right, I'm back. And before I show all of the forces, I just want to show you how I found the gravitational forces. It's force of gravity times the cosine theta, which is mg cosine theta for the perpendicular, and then mg sine theta for the parallel component, as shown in that triangle right here. So we should end up with both because 45 degrees, we get equal sides. They're both 34.6 newtons. Now in the other one, you might get tricked by thinking that you should use cosine for perpendicular and sine for parallel, but the angle is actually in a different place, so you have to think through the problem and see that, my perpendicular component is actually on my opposite side of my angle, so I need to use sine for my perpendicular value and cosine for my parallel value. So when you do that, you should get 5 newtons in the perpendicular side for the force applied and 8.7 for the parallel side. And let's find our net force, right? So actually we can automatically find our R value because the two perpendicular components of applied and gravitational are both acting downward and my reactionary force is acting upward. So my R is going to equal 34.6 plus 5, and that's equal to 39.6 newtons. And that means that my net force, well, we already knew this, net force in the perpendicular direction is 0 newtons because it wasn't going through the floor or wasn't being lifted above this plane. So that's done. But we really then need to find our net force down or up the slope, so parallel to the plane. So one thing to recognize is that these two arrows are acting in opposite directions. So we need to decide which direction is positive and which direction is negative. I personally just try to make it easier and say the largest number is positive. So to make sure that our acceleration is eventually going to be positive and so forth. So I'm saying that since gravity is going to win out on this force, that this down the slope is going to be positive and up the slope is going to be negative. And so I'm going to say that my net force in my parallel direction is equal to 34.6 minus 8.7. And what is that? That's 25.9 newtons. That's my net force in my parallel direction. And then, therefore, the object should still be falling down the slope. And so my net force, calculate the net force, it's all the way over here. But I ended up with 25.9 down the slope. And so calculate the acceleration. Well, my acceleration is equal to my net force divided by my mass. So it's 25.9 divided by 5. And that's going to be around 5 meters per second squared, falling down the incline. Okay. So it wasn't actually pushing up the slope. This is a harder problem, but really what we're doing is we're taking forces at angles and applying it to inclined planes where we have to pretty much tilt our head and change our the angle in which we're framing ourselves. So it's not much different than before. The hardest part is identifying this force of gravity triangle and recognizing where we get the angle from. So the most valuable way to see it is that the forces from the gravitational force on an inclined plane here are either going to act down the plane and perpendicular to the plane. So the gravitational force is definitely going to want to push the mass down the plane. So you need to create a triangle there. The biggest mistake you'll make is if you see this triangle and let's say this is your force of gravity, like I'm just moving this line over, and a lot of people like to do this, even though this is the slope. But when you do this, this value, that component of that triangle means nothing to us. It's horizontal, but our plane, our mass is not going to go horizontal because there's a plane, there's a ramp in the way of that. So that's wrong. That's wrong. We don't want that. So let's just erase that and just know not to do that. All right, it's already 18 minutes in. I'm going to give you one more problem. This I think actually might be easier than the previous problem. So I want you to do this on your own. And I'll pause the video, I'll do it, and then I'll show some steps to get to the end. So assume both masses are in equilibrium. The surface is frictionless, and mass 1 is 2.5 kilograms. Draw a free body diagram for both M1 and M2, and then determine the mass of M2. The keywords here are equilibrium, so we know the net force is 0. We also know mass 1 is 2.5 kilograms, and it doesn't say it, but in the diagram we have a 28-degree incline. So I'm going to pause the video. In 5 seconds, I will show you my free body diagrams. You can check them on your own, and then I'll give you some time to work on them to find the mass of mass 2. Okay, so I've drawn my free body diagrams for weight 1 and weight 2, or mass 1 and mass 2. And some key pieces that I've done is I've drawn my normal force and my tension force for my mass 1 at certain lengths because I know that both mass 1 and mass 2 are in equilibrium. So I know that the normal force should be equal to the perpendicular component of my mass 1's weight. So this is going to be equal to this. Let's draw it as a straight line. And the downward or my parallel component of force of gravity acting on mass 1 should also be equal to my tension force. So I've drawn the tension and normal force with these lengths to match the force of gravity vector that I drew. I also know that the tension force acting on mass 1 should be equal to the tension force acting on mass 2 because it's the same string. So I also know that that tension force acting on mass 2 is right there. And then therefore, I also know mass 2 is in equilibrium. So that force should also equal the force of gravity acting on mass 2. And that this situation is occurring because they're in equilibrium. So this doesn't always happen. It's just because they're in equilibrium that this is going to happen. Now I also know that this value is 28 degrees because of the inclined plane. So now I challenge you to calculate the mass of mass 2 using this situation. I'm going to pause this in a few seconds and go ahead and work on it. All right. So I have identified a perpendicular and parallel calculations order. If I calculate my perpendicular, I end up finding that my perpendicular component of mass 1 force of gravity is also equal to the normal force, which is 21.6 newtons. But that doesn't help me. That just tells me that the net force in the perpendicular component is the same. This may help me if there were friction on the inclined plane, because I know that normal force is included in the frictional force. But I said it's frictionless to make it easier, so that just kind of stops there. So I need to find my parallel component of the weight of mass 1. So I do that m1g sine theta. And then using my free body diagrams, I know that the force of gravity acting on mass 1 is equal to the tension force, which is equal to the weight of mass 2. So I can say the parallel component is equal to tension, is equal to the weight of mass 2, and the weight of mass 2 is equal to m2g, and I can end up finding out the mass of mass 2. And does it make sense that mass 2 should have less mass? Yeah, because all of mass 2's mass is going towards this downward force of gravity, where only partial amount of mass 1's force of gravity is acting against mass 2. So you need a heavier mass 2 than mass 1 to make this an equilibrium. And we're done. I will see you in class. Please add questions to the questions document.